people. Don't overthink this. Did I give you a function that you can use? Did I give you a function? No, I didn't really give you the equation for this function, right? I gave you some inputs and outputs for this function. That's all you need. In fact, that kicks ass. You don't have to throw anything in anywhere. You just look at the numbers. What's going to go on the bottom here? 2, because it's 2004 minus 2002. 2. So over the course of 2 years, how much did crime change? I mean, that's the whole idea here. So what was crime in 2004? 76. And what was crime in 2002? 89. Be careful, don't always make your answer positive. You want this to be negative because it's decreasing. You want to show a decrease in crime. Say, I've implemented these measures where we just throw people off the island if they do something in crime. We're surrounded by great white sharks. Crime seems to go down if you start doing that. So here you got -7 over 2, so it goes down about 3.5 per year there. Yes, ma'am.
I'm a little confused. Why wouldn't you add all the crimes from 2002, 2004, and then divide it by 3? Why wouldn't you get the average of the crimes?
I want to know the rate of change. I don't want to know the average. That would find the average number of crimes per year. I want to know how much did crime change per year.
Divided by 2.
Why divided by 2?
Well, the bottom. I get the bottom, the 2004 minus 2002.
Cool.
But you're subtracting 76, 2004 from 89.
Which makes 13, right? That's it.
Oh yeah, 13. Sorry, I was thinking backwards. 6.5. Cool. 13. Thank you.
I was wondering why.
Oh, you're wondering why it was 7?
No.
Okay.
Yeah. Never.
That would have been legitimate because I decided not to do that correctly. But do you see why it's the way it is? I mean, crime definitely decreased. I can't just do an average number because that would just give me an average per year. I want to know the change, the average change per year.
Okay.
Cool. So it could have went. Why does this number not matter at all? Because if it went crazy, if it went up to 1,000 crimes that year, it just went crazy. That was the year of the riots or whatever, and then it came back down to 76 here. Well, the change from here to here would have been crazy big, but then the change from here to here would have been crazy big negative. So overall, it would still come out to this average per year. Does that make sense? That's why this middle number doesn't matter.
Okay.
It could be whatever that wants to be. Okay, hopeful. And then the same idea here, right? What goes on the bottom there?
2006 to
4. And then 2006, it's 49. 2002, it's 89. All right, I can do that, the subtraction. Good job, Jeff. So that's going down 10 a year. So we implemented the shark thing around here. It really, people realized here, I don't know who the hell it is doing still going. Feed you to the sharks, they're like, they don't care. All right, that's the famous feed to the sharks problem. Is that cool? I mean, that's the last way they can give it to you. Give it to you in a graph, find the outputs and the inputs, find the slope. Table, outputs, inputs, find the slope. Function, outputs, inputs, Find the slope, I mean, it's the same idea. Sweet. So now we get into a very important section. Transformations. Section 2.5. So again, it depends on your teacher how much you did this, if at all, before. Here's the basic idea. Let's start off with something we really should be pretty good with. Here's your good old basic parabola. Where would the vertex of that parabola be? 0, 0, right? Because it just sits right there in the origin. But when you throw a 0 in, a 0 comes out. In fact, think about it this way. What's the smallest this number could be? The smallest I can get if I square something. What's the smallest I can get if I square something? 0. So the whole thing is about where does it equal 0? Where does the alpha come out to be 0? So watch what happens. So here's what the basic graph of this looks like. So you got a point there, point there, point there, and then you connect with the U. So these are your three kind of like anchor points. Okay? Stay with me now. This becomes a little important. So what happens if I do this? So I can hear some of you guys, I know you've done this before because you use the right terminology. It shifts in some direction. Probably the direction you're not considering if you haven't done this before.
Doesn't it go like
Because look what happens here. Here, how do I get 0 out? I throw a 0 in. Here, the first thing I do to my inputs is I take 2 away from it. So what do I have to throw in there now to get a 0 out? A 2. I've got to, all my inputs have to be bigger than they used to. So this whole picture should get up and move that way. Everything has to be 2 bigger to have the same output as it used to. You guys kind of see? So it's reversible. When you see a minus, you actually have to think it's the opposite because it's in there with it. To overcome that -2, all my inputs have to be 2 bigger. So what it's going to do is it's going to take this base graph. It's going to take every single point and shift it over 2. So that point goes 1, 2. That point goes 1, 2. That point goes 1, 2. And then you just draw the picture on top. Yeehaw. That's exactly what I want to see on a quiz, homework, test. The base function, and then move it. Okay. So I can tell from the look on some of your faces who's done this and who hasn't. Some of you guys are like, oh yeah, I got you. And some of you are like, another one. So what about, and it doesn't matter the function. It really does not matter the function. If I have, let's say h of x is square root of x. What does that look like? It looks like a u that's fallen over and lost its bottom part, right? So it's going to be at 0, it's 0. At 1, it's 1. At 4, it's 2. So there's that kind of like part of a parabola look to it. Do you see? So it's a parabola that fell over, and it can't be here because the square root can't have negative output, so that's why it's only up there. Okay, so we definitely should know that, the look of a square root function. So what's going to happen to this if I do this? Oh shoot, I use the same, oh, too bad. So if it's in with the variable, it's the opposite of what you see. All my inputs can now be 3 smaller than they used to be, right? Here, this starts at 0. Here, can't I go below 0? Because the first thing I do is add 3. So what's the smallest x I can put in there now? Negative 3. So this whole thing gets up and goes back 3. Not a big deal. So now I can start with a base graph, 0, 0, 1, 1, 4, 2. There's the base graph. And then you just take every point back 3. Back 1, 2, 3. Back, where are you point? You should be up there. Back 1, 2, 3. How can you kind of check yourself here? Check yourself. When you throw a 1 in, what should come out? Sorry, I should never do that. When you throw a 1 in, what should come out? 2. So what do you get when you put a 1 in there? Square root of 4 is 2. Do you guys get that? That's how you can check yourself. You take a point that you moved, make sure that point actually comes from this. That's a very quick check you can do. Cool. Okay. Don't just make a table of values, by the way, and then, no, you got to actually draw the base function and move it. Okay. So what about, let's look at some other transformations. What about, let's see. What's the absolute value look like? V, I like it. So negative 1, 1, they both go to 1. But it's not parabolic because it's not squared. So V. It's not squared. What here? So the other kind of transformation, the other basic transformation you could do is, let me see if I can throw 2. Well, let's see. Yeah, I'll try to throw 2 at you once. So what's that do? Moves it to the right 1. Now that would show a V. That would be a V. In fact, let's do this in steps. The first transformation would be right 1. Let's do that. So here's the base graph. Negative 1, 0. There's my base graph. Okay. Shift it right 1. So right 1. Right 1. This is exciting. So that's still not my final graph, right? You guys, am I with me? Is that cool? Okay. Now, what's this guy do? That's the V in purple. That's all the outputs for the V in purple. Now, all those outputs will now become 2 bigger, so the whole thing goes up. Is that 2 inside with a variable somewhere?
No.
Here's the really cool thing. I want you guys to see this. Isn't g of x just y? Remember? Back in the day? Stay with me now. I want to show you this. Can't I subtract 2 over? So now it's going to go right 1. Remember, it's kind of the opposite of that. Being 1 bigger, so go right 1. And up 2. It's the opposite of that now. If you wanted to do that, you could. As long as the transformation is with a variable, it's always the opposite of that. Now, I kind of don't like that way personally. I just want to show you that in case you like it. This just makes more sense to me. There's that. Now take that up 2. Whoop-de-doo. Right, all the outputs are now 2 bigger than they used to be. So what's my final thing going to look like? Just take all these purple points up 2. 1, 2. 1, 2. And 1, 2. So there's my final graph there. And to check it, if I throw a 2 in there, I better have a 3 come out. 2 minus 1 is 1, plus 2 is 3. Yay. How are you guys feeling about that so far? So you can see why I made a big point last time about you need to know what these things look like. If you don't know what they look like, you can't even do first step. Sure, you guys try this one. You have this here. Let me start over here. Throw you in. Well, let's just do that. Then we'll talk about some other transformations. base function first?
I found it a while ago.
Oh, I like it.
Uh-huh. It didn't print out on the bottom part, but not that you want.
What has happened?
It's the different, it missed the formula on the bottom, but.
Oh, okay.
So, except for test purposes, you notice the little dotted ones first?
Yes, I need to see those. In fact, I normally will ask you, I think I forgot to do it on the practice test, but I'll ask you to list out the shifts. And so it'll make it easier for me to tell what you're trying to do if you make a mistake in the graph. I can at least see, could you tell what the shifts are supposed to be? Which kind of reminds me, let me give you these real quick. So I'll have an answer key to this next time.
Yeah.
Alright, so of course the base function looks like what? U, cool. And what are the two transformations here? Right, 3 up 4, cool. So you go, and let me show you, you don't necessarily have to do the intermediate, especially when it's nothing all that major here. So write 3, 1, 2, 3, up 1, 2, 3, 4. Write 3, 1, 2, 3, up 1, 2, 3, 4. And then you know by symmetry this will be there. Sweet. Okay, cool. And of course, again, to check yourself, when you throw a 4 in there, it should come out with a 5, right? 4 minus 3 is 1 squared is 1 plus 4 is 5. Yay. So you always have a way to kind of check yourself, make sure it's in the right place. Okay, so that's not overly evil, right? Not yet? Okay. So what do I want to throw negatives in the mix? Negative square root of x, let's say. H of x is negative square root of x. Now square root of x, the outputs have to come out positive, right? So all this does, if there's a negative on the outside, who can describe what that would do graphically, visually? In which way? There's a couple of different ways you can reverse it. All the outputs will be not what they used to be, but they'll be the negative of what they used to be. So it actually flips around the x-axis. If I put the negative on the inside, it would do what you're saying. So what this will do is, here's the square root. So here's the square root. And of course what this does is, that's 1, it becomes negative 1. That's 2, that becomes negative 2. So now it just becomes the other missing half of that dude, right? You guys with me? Which kind of makes sense. That's the principal root, and that's the missing root. You guys remember that? I don't know. There are two roots of 49, 7 and negative 7. Because negative 7 squared is also 49. That's the principal root, and there's the poor little missing root, the negative part. Okay, maybe that was too much. I don't know. So like I just said, if I throw a negative on the inside, what's a more interesting one? I don't know. Oh, sorry. What's happening? Let's do that this way. Now, when you first look at that, your brain might rebel a little bit because you're like, can't take square root negative. You know, we don't want to graph complex numbers. I don't blame you. But this does not come out complex as long as x itself is negative. So I used to only be able to put in positive numbers because I can only take the square root of positive numbers. But now if I get the square root of negative something, I've got to throw in negative numbers so that at the end they become positive. And then the square root can do its job. So negative on the outside is a flip around the x-axis. Negative on the inside is going to be a flip around y-axis. I love it. So it would take the base graph and it would flip it this way. Every point now becomes there. That point becomes there. Yeehaw. So here's something interesting. If you wanted to do this, oh yeah.
Put it in the corner.
What do you think the last shift you should do? Yeah. Because you got to know what that is before you can make it go up too. So that makes sense. That's pretty much that guy by himself is almost always going to be the last thing you do. Yes. Oh. So yeah, what shifts do I have? It's got to flip around the. Yeah, flip the x-axis. Flip y-axis, and then finally up to from wherever the hell it ends up. And you kind of know where it's going to end up. If I flip the x-axis and then flip the y-axis, it's going to look like that basically, and then I just take it up too. So you have a rough idea of what it's supposed to do, and then you can attack it for real. Here's the base graph. Here's enough for the base graph. So flip the x-axis. Would be here. Flip the y-axis would be the color for this here. You could do it, Jeff. There we go. And finally, take that. Every point goes up 2. This point goes 1, 2. This point goes 1, 2. Funky deli. If you have your graphing calculator, well, that's the ultimate way to check yourself. Throw that thing in there just like it is and see what it looks like. But to check ourselves by hand, if we put a -1 in, we better have a 1 come out. -1, negative 1 is 1. Square root of that is 1. -1 plus 2 is 1. Thank God. Okay. Cool. So here's the final kind of transformation. This is one you should know a little bit about. What was it with the number that was in front of a parabola, a quadratic? If I put a number out front like 1/2. That 1/2, who remembers what that would do? Would it become, there's different ways to say, would it become wider or would it become narrower? Wider, because it's sort of like, it's still sort of like a slope. It's going to go up half as much as it used to. So every point is going to be half as much. So it used to be here, well now it's going to be there. So it's going to become wider. If I put a 3 in front, that's going to become very narrow because now it's shooting up faster than normal. So what shifts are in this? Shift, right, 3 and cut outputs in half. It's also called a compression, but because you're pushing on it, right? Or it's an elongation on the x direction. You can look at it 2 different ways. I'm not too worried about that. Just cut them all in half, and that'll get you there. So if I do this, I think we can shift right 3 pretty quickly. Here's my base graph. So shift right 3. And finally, if I cut everything in half, this will be halfway down. This will be halfway down, and this will stay right where it is, right? So that's why it becomes wider now. Cool. So you can imagine, I could throw every single shift that you have. I have a negative 7 on the outside, negative on the inside with a plus something at the end, and all this kind of stuff. You just have to list all those shifts for yourself first, and then start doing it. You can always check yourself a couple different ways. Oh, so that's if a number's on the outside, that's going to affect the output. So it's going to be a compression or something in the y direction. If I put a number on the inside, so for example, I do like that. Now let's make it. Watch out, yeah, that one. Because you can do the square root of 4, you can make it a 2 in front, but no way to do that. So if I do this, now it's going to affect my inputs, right? So now all my inputs can be half as much as they used to be. You guys still kind of with me? So see how when it's, I don't know if you guys get this general theme, when it's inside or with its variable, when it's with the variable, it does the opposite. Isn't this doubling? Well, what does it end up actually doing to the picture? It's going to make it half. When it's outside, when it's not with the variable, it actually does exactly what it said. It does directly cut it in half. So how would this thing look? We got our square root. No joke. And now, for example, here I had to plug a 4 in to get a 2 out, but now what do I plug in there to get a 2 out? 2. So it actually cuts all of my inputs in half to get the same output. You guys with me? Because the first thing I do is double the input. So I used to have to throw a 4 in to get a 2 out. Now I have to throw a 2 in to get a 2 out. Twice 2 is 4, square root of 4 is 2. I don't have to throw a 1 in there, I have to throw... When I throw a 1 in, I get a 1 out. Now how do I get a 1 out? A half. I throw a 1/2 in there, right? 1/2 of 2 is 1. So 1/2 now goes to 1. 2 now goes to 4. So this one pushed down on it, didn't it? Compression. That's why it's compression. So the guy went, ugh, crap. This one presses that way, towards the y-axis. Compression. You guys semi with me. All right, a little bit. Okay. For some reason, I remember that scene in Hancock when he pushes on that metal thing. You guys ever seen the movie Hancock? Or is it just me? Do you remember that? Has it been that long now? Will Smith, superhero? Actually, possibly a god at some point. Okay. Anyway. So obviously in this section there's going to be a lot of graphics. So help me out. If I were a student in my own class, I would require me to use graph paper. You can see why. Me on paper sucks with graph. So you know yourself, if you need graph paper, get it. In fact, we're going to do a lot of graphing in here. So buy bulk. Go in with somebody else. right? Get some graph paper. You can actually print it out from the internet, but then you still need paper, so you still got to spend some money somewhere. Okay.
We should make a stamp for it. A graph.
Oh, a stamp? That'd be interesting.
Makes more sense.
I don't know.
Then I could just put it right on my hand.
Like a little stamp. I like that. You can put it wherever the hell you want to.
Mm-hmm.
I'm sure somebody's got it.
Must be out there.
If not, start it up.
I think so.
Graph stamps are us.
Mm-hmm.
All right. Let me do just let me give you guys one more problem to try on your own here. Let's see what you think about this. I'm going to give you one that's a little different than what we've done so far. So here's the graph of f of x. Graph f of x minus, let's see, plus 2 minus 3. That's fine. Would do that to myself, wouldn't I? Yeah. And whenever I give you a little something to work on like this, you can certainly compare notes with somebody sitting near you. Nothing wrong with that. You get this? No. let me look at this first guy here. What are the shifts involved here?
Left 2.
Yeah, back 2,
Down 3.
down 3. So you can see I had to adjust my stuff a little bit. So every single point's going to go back 2. So this guy's going to go back 1, 2, then down 1, 2, 3. Let's see, back 2, 1, 2, then down 1, 2, 3. Back 2, 1, 2, and then down 1, 2, 3. And then back 2, and then down 3. Cool. You can draw that shape back in. So the whole thing just picked up and moved down and back. How are we doing so far? Not too bad. This one's a little bit freakier. What are the 2 shifts here? What does this stuff on the side do? What does it do? All my inputs can now be, or now have to be what?
Twice as big.
Twice as big. So it's going to be like an elongation. This guy was pushing on him. This guy's going to elongate it. Okay. So you have an elongation or a compression in that case. All you got to do is think to yourself, if it's just X to get 4, I put in a 4. But now what I have to put in to get a 4, I have to put in 8. Twice as much. So all my inputs become twice as big. And then I can do what with it? Flip it. So, let me see if I have anything crazy. No, good. So, to get to this output, my input now had to be 2 before, but now it has to be 4 to get to the output. How are we doing so far? You okay? And of course, this is not going to be my final answer because I still have to flip it. And then, so do that with everything. This was 1 input to get here, so now it's got to be a 2 input to get there. The neat thing about that guy, the input had to be 0, and now it has to be 0 to get there. Kind of with me? No. If I have a, let me see. Actually, it would be good to use. All right, this is going to be a neat part of the video. So you guys ever seen this kind of thing before? I love this thing. If I elongate this and I pull both sides, does the middle do a damn thing? All right, that's what I'm talking about, right? If you're right on the y-axis, sorry. If you're right on the y-axis and you're doing you're pulling it along the x-axis. Now I can't get it back to where it was. Stay. This guy, of course, is going to stay right where it is because you're elongating it like this. So of course he's going to stay right where he is. Maybe. So what's going to happen with back here? This guy's now had to be a -2 to get here. Now he's got to be a -4 to get there. So here's my intermediate step. Let's see. You can do it, Jeff? Oh, yeah. You can still do it. There it is. Okay. Woo. Yeah.
Why did you put the point on 4 and 3? Why did you put the point on the first point?
Oh, here.
Yeah. How did you get it?
An input of 2 used to get me here, but now I have to have a twice that to get there. Because now a 2 input used to get me to the output of 2, but now I have to put in a 4, because what's the first thing I do to that? 1/2 of 4 is 2. So I have to have a number here. Let me do this specifically. For x equals 2, for the original thing, what's the output? 2, right? So now I still need this thing to be 2. I still need my input to be 2, which means x now has to be 4 to get the same output as before. So how do I make this inside a 2? I now have to put a 4 in. So that's why that just doubles up to 4. That doubles down to -4. Yeah.
So that 3 just stands still, doesn't really move anymore.
Because 0 doubled is 0. Right? This is the input of 0. It's going to stay right where it is.
Alright.
And that was the point I was trying to make there. If I pull both sides, the middle stays right where it is. It's only stuff away from the middle that moves out. Okay. So like the expansion of galaxies, but not really. All right, and then the last thing I got to do before I can get it done is flip it. So that's a nice, beautiful little like reflection thing, right? That reflects down here, bam. This reflects up here. Where am I at? So there, that's good. And this reflects down here, and this reflects up there. Okay, I've just got a little too much going on in the same picture, so excuse me for that. But you guys kind of with me?
Mm-hmm.
Obviously, on your homework, don't try to do too many problems on the same graph. Yeah.
If it had been negative 1/2 x, it would have flipped over the.
Oh, if it
y.
would have had a 1/2 out here?
No. Instead of having the negative x,
Oh,
it would
like
have been
in
negative
here
x.
would've been
It would
like
have
that?
flipped it over the y-axis, right?
Yeah.
Okay.
Because now all my inputs would have changed,
Right.
and my outputs would have stayed the same. Here, all my outputs change.
Gotcha.
Good. Because that is where it was with the blue dotted line, right?
Mhm.
And now all the outputs become the opposite of what they were. So
Right.
it just flips right over.
Okay.
Cool. Maybe. That's not too evil at all. As long as, if you list for yourself what the transformations are, that'll be a big help for yourself. And this is a really good time to get used to your graphing calculator to check your work. Get your final graph and then plug the actual, well, especially if they give you a function. Here they didn't. But if they give you a function, plug the actual whole thing in your calculator and see what it's supposed to look like. Yeah.
We often like the function expand because we add half in the middle, or for with x, or because we have like fraction, or because we have a number.
So it got bigger because it's a number less than 1.
It's fraction. Technically, it's fraction.
Yeah, it's a fraction. I mean, a fraction could be bigger than 1, but it's a,
Yeah.
yeah. You guys with me? So if I would have put a 3 in there,
So it will,
that would have compressed it, right?
okay, what is number outside the x?
If it's out here,
Yeah.
then that would be truly what it says. So if it was a 1/2, it would take all the outputs and make them 1/2 as big. Cool. Okay. What you got to realize is when it's in with the variable, when it's in with the x has to undo this thing to keep things the same. So if I want a 2, I now have to put a 4 in, because the first thing I do to the poor dude is cut him in half. That's why this type of thing happens. And if any of you guys have ever taken any physics or you do any music, sound engineering, and you know about sine waves, that becomes very important. You compress a sine wave, you change the frequency. So if you want a certain frequency, you got to kind of know how this math works to be able to get there, right? Okay. One last little thing, and then I'll let us out here just a little bit early. Oh. And this is nothing major, thank God. Let's see if you guys agree with me. You're all like, yeah. What's your nothing major, Jeff? Oh, let me just give you the problem. See what you guys think. Let me just stop right there. I already heard a scoff. This is nothing major. What does your gut tell you to do with this? I mean, if I ask you what f of 4 is, and you make that sound, I'll be a little scared, right? There's more going on there. But what's f of 4? How do you get f of 4? Plug a 4 in. How do you get g of 4? Plug a 4 into g. So what is this really asking you to do? To write it in a better way, it's f of 4 plus g of 4. Right? So it's two little simple problems. What operations can I put in there? Addition, subtraction, multiplication, division. Okay. Is it 2.6? No. I don't think it should come out to be a...
No.
Oh, is this section 2.6? Yes. It's like, how the hell does that become 2.6? You're right, it's section 2.6. F of 4 is 2. All right, 4 plus 4, 8 divided by 4 is 2. G of 4 is 14, so this is 16. If I would have put a minus, you would have subtracted. If I would have put a FG, they're sitting next to each other, so that means multiply. You would have multiplied these two numbers, right? This is what I mean by nothing major. Do you guys agree with me that that is definitely nothing major? Okay. So what if I ask you? This is one problem here. Come on. I'll for you guys. You're awesome. What if I said f of g of 1? Yeah, you have to work from the inside out, just like order operation says do inside the parentheses first. So I don't know what I'm throwing into f. I'm throwing whatever the hell g of 1 is. That's what I want to throw into f. So I got to first figure out what the hell is g of 1. So what is g of 1? 0. And what's f of 0? Say it. Undefined. I like it. Cool. So you won't always get nice answers. Because you can't divide by 0. Cool. How's that? So this is what's called combinations of functions. You can add, subtract, multiply, divide. You can do, oh, the thing just went out of my head. You can plug one function into the other one. Composition, there it is. Compositions of functions, right? In fact, if I really felt like it, I could do a problem like this. Let's see if I ever feel like it. So to do this, and then do that, and then do that, and then, that's more of a busy work, but maybe I'll do that much. Yeah?
Can't the square root of 1 also be negative 1?
No. Square root of 1 is understood to be the principal square root, which is the positive root. If you want the negative root, you got to actually put the negative one. That's why the square root only has the top part, not the bottom part. All right, that's plenty, guys. So I'll have the quizzes graded next time. I got that group work thing. I forgot to give it back to you. So if you want it back right now, otherwise I'll give it back to you next time. If you want it back, come up and grab it. I didn't really grade it. I just put some notes on there. It's alphabetical. So.
Thank you.
Yep. I'll show you. What's your name? Mom, right?
But it's good because the library rents out graphic design for the whole week.
Oh, look at that. Good time. Come on, work. Yes.
Being up there all day. Sam Roberts.